Okay. Welcome back from spring break. Hopefully everybody got a little rest. We have you should turn in your homework 4s. We have your midterm, your homework 3, and a bunch of old stuff here to pick up. So today's St. Patrick's Day. A couple of you are wearing green. I'm wearing green. That's kind of the main thing, except for beer, and we don't do beer in class. So, but last week was Mardi Gras, or week before actually. And so I'm actually originally from New Orleans, where we have parades. And the parades in Mardi Gras are quite different than like the parades here for St. Patrick's Day or whatever, in that they throw beads from the floats. And so I brought some, so everybody can have a bead. So yeah, I would normally just throw it to you, but then people get hurt. And so you'll have to pick that up. Should be enough for everybody. Normally I would have done that, the other time, but it was during the midterm and that didn't seem like very much fun. Okay, so on homework 3, which is graded, Jeff had some observations in terms of how everybody's scrolling techniques did. Surprisingly, the standard scrolling now that everybody loves with 2 fingers on a touchpad did not do very well in general, except for some reason on the iPad minis, which was a little surprising that it should be different. On Macintoshes, it worked okay. Generally, a mouse wheel with notches so that you could feel the increments worked the best. People using the keyboard arrow keys was very accurate but slow. So pretty much as we expected. Homework 4 is due today, and we should have those graded within a week. People did pretty good on the midterm, a little bit disappointing. I was hoping more for an A-centered, an A average, but almost everybody got Bs or As, and there's a few people who really could have used some more studying. So I thought I'd go over the answers to the midterm for people who didn't quite get them right. Let's actually bring up the midterm. Okay. So defining interaction technique, there was a bunch of definitions in lecture 1, obviously, even on the course webpage. Most people got it right. I was basically looking for something that showed that you knew it was an input technique and an output, so it had feedback with respect to what happens, and that it was some sort of small thing. So if you just said it's a way of performing a task, that was too vague, too high level. It had to be something about an elementary task or a small task or a single way of getting a piece of data or something like that. Which of the following are interaction techniques? Scroll bars. Scroll bars, right? Microsoft Word. Everybody got this one right. Menus, yes. A chart like this, no. Animations, no. Animations have no input. It's purely an output technique. A couple of people got that one wrong. A way to type on a smartphone, yes. On-screen button, yes. Physical button, like on a remote control, yes. Dashboard widgets, people were confused by that. It was explicitly in lecture 1 where it says that dashboard widgets are not examples. It's basically a whole application. They just use the word widget. And then selection handles is yes. So which of the following hypotheses are good? And almost everybody got these right. A good hypothesis has high specificity. It's expressed in a positive way. It's something you can explicitly test in terms of the user study. So the first one is good. No, the first one is bad because do worse is vague and something else is completely unclear what you would test it against. The second one is good it's very specific about what you're going to test. The third one is vague because it's negative and it's not clear what it means to be sleepy. That was kind of unclear. Worse is also not clear what dimension you're going to be measuring people on. The third one is also bad. Again, another is vague. You don't know what you're testing against. And like, may is, you can't really test whether they may do something. You have to test that they do something or don't do something. The final one, I actually accepted both, positive or negative. We were expecting it to be positive, but a number of people said that it was negative because studied is unspecified about how much study one has to do in order to count in that position. And so if you said that, then that was also accepted as a correct answer. So why were early pen-based computers worse than the iPad? And people had lots of really good answers for this, some of which I hadn't actually remembered. So that was fun. So what were some of the reasons that you guys gave for this that were marked as correct? This is audience participation time. Yeah? Right. So one of the obvious ones is the handwriting recognition was poor, and that really deterred people from using it. What else? Battery life. It was really heavy and slow, and it only lasted for a couple hours. Yeah.
The early systems required a stylus, which meant if you lost the stylus, then...
Right. So they required a stylus, which you had to pull out and use. It made it awkward to use in different situations. And things were small, which meant you needed high accuracy. So a lot of that came out of the dependency on the stylus. What else? There were lots of other things that people wrote down. Yeah? Yeah, so, right. I mean, all of these systems were designed to have other people write programs on them. But in fact, very few people had. When they were released, there was virtually nothing else. One of the big advantages that the iPad had that a number of people mentioned is that it started with the entire iPhone program base. So there were all these applications at first launch, even before people wrote custom apps for it. So that was a big advantage of the iPad. Yeah?
It was really hard to connect early systems to the computer when your battery dies off that.
Right. So there's actually a number of different points there. One is that they hadn't invented flash memory, or it wasn't generally available. Flash memory is kind of like a hard disk in that it remembers stuff when you turn off the power, whereas like a regular computer memory, as soon as you turn off the power, it loses everything. That's why when your computer crashes, right, you have to start everything up again. So on the iPad, they use flash memory to remember stuff like what's on the hard disk. And on these early systems, they had nothing like flash memory. So when the computer died because it ran out of battery, it actually forgot everything that it had except for the operating system, which was on what was called ROM, or read-only memory, so that they couldn't put stuff there. So that was one important disadvantage, is that you would load all your stuff on it, and if the battery ever died, then you'd have to start over again, which was really annoying. The second point is that it was really hard that these guys didn't do a really good job of connecting to a PC, and so that was one of the things the Palm Pilot actually innovated and did really correctly, and obviously the current systems do really well, is sync really well with PCs so you don't lose your data if the system crashes. The other point about communication, of course, that some people brought up that I hadn't actually thought to mention was Wi-Fi, and 4G or 3G is generally available now, and of course it wasn't back then. And so you always had to connect with a wire, which was awkward. Of course, there was nothing like Bluetooth either. What else do I have? Anybody have something else that we didn't mention? That was most of the things on my list. Oh, it wasn't color, so it wasn't as pretty. Some people mentioned how pretty the iPad is, so it's very attractive. Anything else anybody had? Okay, Which of the following did Larry Tesler invent? Copy and paste. Yes, everyone remember that. The idea of having an on-screen scroll bars for scrolling. Nope, he did not invent that. In fact, we can't really figure out who invented that. I don't know if you saw my email over the break. I was interviewed by somebody from the New York Times. It's got a lot of publicity. They were wondering where scroll bars had come from. And we know that there were scroll bars on the Macintosh. And so I asked Larry if he knew where they had come from, and he said he didn't remember. And I asked Dave Smith if he remembered where they came from. And he said he was pretty sure they were not on the Star, but he didn't know where they had come from. So it's still a mystery who invented on-screen scroll bars. Somebody, I asked some other groups that I'm on, and said they thought they remembered seeing them on old teletype machines where it would actually have a percent, it would go across the screen with stars or something. Since the beginning of computers, they've always had blinky lights, right? And they've had printing out dots as they're making progress. So the idea of showing that they're working and not crashed, which I called in my article random progress, or you might see the spinning ball kind of thing, that's been since the beginning of computers. But the idea of having an actual progress bar where you know what percent you are done, we have no idea where that came from or who had invented it. So that's kind of interesting that piece of information has been lost to history, and maybe somebody can figure it out, but so far we don't know. Putting the text cursor between characters, that was something he mentioned that he invented. Before that, the cursor had always been a selection of a character, and it was actually that way on the Star, that anytime you clicked somewhere, you got a whole character selected. So it wasn't clear if you typed whether it would go on the left of that character or the right of that character. Doing user studies is a way of refining user interface ideas. Actually, Larry Tesler takes credit for being the first one to actually do that. He did that way back when he was in school in the early 70s or 60s, I forget. And he brought that idea to Xerox PARC and did that on his early systems there, which end up being used in the Star and now pretty much everywhere else. Selecting objects before specifying the edit operations, that's basically the standard thing that he did to avoid modes. 3-button mouse, did Larry invent that? A couple of people got that wrong. Who invented the 3-button mouse? So that was from Engelbart, the original inventor of the mouse. His mouse was 3 buttons. And if you remember, the 3-button mouse resulted because they wanted to have a gazillion buttons, but they couldn't fit them in the little box that they built. And so 3 was actually the maximum that they could fit, and they used that on all the old systems, the original mouse from Xerox PARC and so forth. So 3-button mouse was much earlier. The goal of modeless operation of a computer, again, that was something he talked about a lot. And then finally, the keyboard key label props for properties. Was that Larry Tesler's? Who remembers where that one came from? Yeah?
The Star.
Right, so that was Dave Smith. That was on the Star with the physical keys on the keyboard. And I don't know, for those who missed some of these, as you were going through the rest of the test, there were hints of some of these answers and some of the other questions later, so you could have gone back and probably fix this answer. So what was different between the Star and the way we do things now, and what was the same? There's an awful lot of choices here. Most people got most of these right. And again, some of these are actually represented in future questions. So what were some of the differences?
Create by copy.
Right, so there was no way of creating from a blank screen in the Star. They had a list of templates or I forget what they call them. I think templates. Transfer sheets. They were trying to use terminology that people might be used to back then, so that you would have to copy things from that. Yeah, good. What else? Lots of choices. Most people got a long list of these, so come on.
Icons in Star were copied but never created.
Right. So it's a similar thing that you copy icons to make new ones. You don't make new ones from scratch. There was a bunch of things about the icons people got right. Yeah.
Icons like represented like actions you could perform on stuff. So like sending a document to someone else. Or something.
Yeah. So I counted that one correct. Obviously, which icon do we still have that you drag things to do stuff? The recycle bin or trash can, right? So basically that one behavior has been retained, but all the other ones on the star have been pretty much ignored. So on the star, in addition to doing that, you could, well, the other one, of course, is putting things in folders, which you could do back then and you can still do, but you could, the way you sent mail was to drag things to the outbox, and the way you printed was to drag things to the printer. And so all of those have been removed, and now you do those operations with menu commands. What else? No?
There really weren't very many menus. They tried to keep the list of options very simple, so there was no big menu bar.
Right, so they had a little menu pop-up thingy, which some people mentioned. They did not have pop-up menus in general, and they had no menu bar, obviously. And most of the operations they tried to put on the keyboard as special keyboard keys, or using drag and drop. So they tried to minimize use of menus. So just for the HCI people in the room, so what are the trade-offs with not having all these menus that, what would be the advantage for the Macintosh of having lots of menus, lots of things in menus instead of having them on the desktop as icons or keyboard keys? What are the design trade-offs? Who's an HCI person? At least half of you guys are HCI people, so you should know the answers. Yeah?
I mean, you can access those commands even if the desktop is covered up by other windows.
Okay, so obviously, if you have these giant windows covering everything, it's hard to get to the printer icons, to drag things to it. But the menu bar is always available, so that makes it easier to execute. Yeah?
Smaller is better because you can just swing the mouse at the edge of the screen and no need to overshoot.
Right, so there's good target Fitts law kind of benefits for having the menu bar at the top of the screen, like on the Macintosh. You don't quite have that benefit with Windows because you still have fairly small targets. What else? Yeah?
Well, if you eliminate the physical keys, then the keyboard can be smaller?
Yeah, so the original Macintosh keyboard was quite small, whereas the Star keyboard had to have all these banks of special keys. Another one that I was primarily going for is discoverability, or it's not really obvious how you do print on the Star, right? Because there's nothing on the screen if you're looking around and you're looking at your document and you're trying to wonder how to print it. Then you have to kind of know that you have to drag it to this printer icon, and you have to make sure you have some printer icons around and things like that. Whereas the discoverability of things in menu is quite good. If you hover around all the different menus, you'll see the print command, and then you'll know how to do it. Okay. There are a lot of other differences. The copy and paste model was entirely different. The copy and they didn't call it paste. They just had the copy button on the screen, and then you lifted it up you went into a mode, and then you showed where it would go to. The original Star was tiled instead of overlapping windows, which is quite a big difference. They used property sheets instead of dialog boxes. So some people said that at the top, and some people said that at the bottom. So I took it, correct both ways, depending on if you described it correctly. Property sheets were not exactly the same thing as dialog boxes, but they're pretty close. The widgets actually looked quite different. Nobody actually mentioned that. But the radio buttons and checkboxes that we now use in pretty much everything were designed quite differently. In the Star, if you remember, they put a list of options touching each other if it was like radio buttons, and separated if they're like checkboxes. So that was a very different look. Another thing that I don't think anybody mentioned is the Star did not gray out items. It only eliminated items that weren't legal, whereas the Macintosh decided to gray out items that were not legal in the current context. Things that work the same way, What are some things that are the same, besides what we already talked about? Yeah?
Window controls in the title bar.
Yeah, so the title bar had a bunch of window controls like close and shrink down to an icon. Another one I forgot to mention for the top was the scroll bar had the arrows pointing in the wrong direction. If you remember that here, hopefully you remembered it in the later question. And a thing that worked the same was the rest of the scroll bar, dragging the handle and things like that. What else was the same? Yeah?
Files were shown as icons.
Sure. Files are shown as icons. Folders were also icons. You open a folder and see the list of files in it. Things like that were the kind of whole concept of a desktop. And another one I had was that I don't think anybody mentioned was the graphic selection handles. When you click on objects, you got a bunch of handles around the outside that you could use to manipulate it. And that was the same too. Okay, I guess I gave away the answer in the question because everybody got this one right. If you have a mouse that's where the gain's turned down, it would be slower and more accurate. Whereas if you have a rate-controlled joystick, it'll be faster but less accurate, and you'd probably have a lot of overshoot where you were trying for a target and you went further than you meant to. Some people mentioned, which is probably true, that if the gain is turned up too high, then it really won't be faster because you'll keep missing the target and having to backtrack. So for long distances, you would move faster, but whether it would actually be more quick in general would depend on how big the targets are and how far you have to move. But pretty much everybody got that one right. Most people got this one right. The Ted's guest lecture had just been the lecture before this, so hopefully people remembered. The key point of Ted's lecture was how hard it was to get this right, how much iteration he had to do. He worked for 8 years, trying all sorts of different things. There was a long list of things that he tried. The transfer function, everybody got right, was the mapping between how hard you pushed and how fast the cursor moved. People said that in different ways, but I accepted anything like that. The kind of rubber for the tip, the shape of the stick, where it was located on the keyboard, whether there was one or two of them. Somebody mentioned the size of the associated buttons. He changed a few times, so down here somewhere are some buttons that go with that, and so those were something that he iterated on as well. Did anybody have anything else that they mentioned?
People made the T keyboard as a platform, and then later shifted to the actual platform.
Right. Mm-hmm. And the other thing that somebody mentioned was putting it on the mouse and putting it in some other places instead of also in the keyboard. Okay. Most people got this one right too. It was pretty obvious there's a large number of differences between these that cause trade-offs. Obviously, the main one is that this one can only handle a few items, and this one can handle lots of items. These are faster to get to and all of the items are the same speed, whereas here, some items are a lot slower than others. Some people talked about hierarchical menus and said that one could do them and the other one couldn't, but that's really not true. You could have any of these have pull-out menus, and obviously all of these have pull-out menus. And you could either have these be click-click menus, click to pick one, click to click the next one, and so forth. Or when you move here, this could pop out a submenu. So there really was no difference in hierarchical menus, as far as I know, so I counted that wrong. Both of these are pop-up dynamic menus that can change dynamically, so that was not right either. This can take up a lot of screen space. If you add a bunch of more items, they tend to get bigger, whereas this is clearly fixed size, or it's designed to be fixed size, independent of the number of items. Anybody have any other things they mentioned? Yeah.
Fisheye depends on ordering that the user understands.
Right, yeah, so this is mainly good for alphabetical or some other ordering that's fixed, so that you kind of know what's down here if you want, because you obviously can't read it. Whereas there tends not to be a very good ordering for pi menus except for something that's actually in the different directions, like a compass or something. So it would be really hard to know where things would be if it was a long list. Anything else? Okay. I was really disappointed that some people got some of these wrong. Nobody got this one wrong. Everybody knew that this was Sketchpad. That was good. And everybody knew that this was the iPhone. So I think everybody got those two correct. I was surprised that some people got this one wrong. This is Smalltalk. There's this little arrow here. And it was one particular, but one area went up and a different area went down. I was surprised that people got this one wrong. This is the original Macintosh. It has the the black and white arrows and the resize buttons down here. These two, a lot of people got wrong. That was not as surprising. This is OpenLook, and it had the unique thing where the arrows are on the elevator or on the thumb. And this is Next, which had the unique thing that the two buttons were collected together at the bottom. Also, Next was gray and was grayscale, and OpenLook was color, but you probably couldn't tell that on your version. And then this is obviously the star with the arrows pointing the opposite way. I was surprised that people didn't get that one right, too. Some people didn't know what prefix, infix, and postfix was, which made it hard to get this question right. Prefix means the operator is first. Pre means first. Infix means the operator's in the middle, and postfix means the operator's at the end. So it describes where the operator is. So prefix with the operator first. People came up with lots of good examples of that. What are some examples of prefix operations? Yeah. Drawing tools, where you pick the tool and then you draw. So you're saying rectangle, and here are the parameters to the rectangle, or draw rectangle, create rectangle, and here's the size, and so forth. That would also count as an infix operator, it turns out, because some of the properties like color are chosen first. So if you described it that way, then that would also work as an infix operator. Red, create rectangle, this coordinates. Any other prefix operators besides create? Some people mentioned command line stuff, like on an MS-DOS prompt or Unix prompt, where you type, rm space and then some file names, or del, then some file names. So command lines are always prefix. Anybody have any other prefix examples? What's an example of infix? Drag and drop is kind of the prototypical example. So you say this object, drag it to, and then you say where. So drag and drop is infix. What's another example of infix? Yeah? Insert, yeah. So in a modal system where you have to say, go into a mode and then insert text, why is that infix? Well, if the operation is first, then it's prefix.
Oh, sorry, I was giving you a prefix.
Yeah. So actually, you could say that insert in an old-fashioned editor could be infix in the sense that you say here, so you press the location first, then you say insert text, and then you give it the text to insert. So in that case, it would count as infix. Any other examples of infix? A calculator, 3 plus 4. The plus is the operator, so that's in the middle. You go another one?
A lot of find commands can do infix, where if you already have something selected, then it goes and finds it elsewhere.
Okay, so this, find it again. I guess that's postfix, though. But you could certainly imagine the regular find command to say from here, find, and then type in the string you want to find, right? And so to the extent that the current position in the text is a parameter to the find command, then you could count that as infix. And then postfix is the operator last. Everyone got the same example for postfix, which is delete, right? This thing, delete. That's clear postfix. That's pretty much the one everybody mentioned. Anybody have any other examples of postfix? Yeah? Yep, that's the one we just said. Good paying attention. Yeah, something else?
The grow and shrink font size buttons.
Sure. Yeah, so those are singleton operations. So it says this font bigger. There's no extra parameter, so it's a postfix operation. So which of these did Larry Tesler strongly prefer and why? The answer is postfix because it's less modal. Some people didn't remember the name but still got it partially right because they remembered why. So even if you didn't remember the name and you explained what the issue was, then you got credit. And some people picked postfix but didn't remember about the issue of avoiding modes. In that case, that was only partially correct. Then there was the state transition diagram question. And this actually came right out of lecture 16, or 11, actually. Wake up. So actually, something like this would have been correct. Nothing happened on hover in the current description of this one, so you could leave this state off altogether and just say start when mouse is over and button pressed, when mouse is over and button pressed on the object. But a lot of people lost points for forgetting this state, which was kind of the whole point of the question, is to remember that you have to deal with the case where where you have the mouse down over the object and you move the mouse away from the object and release. Okay? Or you move the mouse away from the object and you can move it back. Right? So if you forgot to deal with the fact that while the mouse is down, you can move away and move back, then that was a bunch of points off. And a lot of people forgot all the arrows going back to the start. If you had a very explicit end state, then that was okay. But if you just kind of left it dangling, then that was also points off. So the basic idea is that everything that happens, you have to have an arrow for. And in the question, it very explicitly gave a hint that a lot of people missed. Note it says, put the event and the resulting action on the transitions, arrows. So this was a hint that you should have had arrows, and you should have labeled the arrows with the event and the transition and the thing that happens. A lot of people didn't do that, even though it specifically told you to in the question. So just a reminder that you should read the question carefully, and often it'll give you parts of the answer. I guess I have to take this off. And if there's Okay, finally, why is it useful to measure both corrected and uncorrected errors in text entry? So remember that corrected errors are the ones that people fix. And in the homework 4, we didn't really have any way of testing the corrected errors except for having you look for them by hand, unfortunately. And the reason to look for those is to try and make sure that you know what's going on. When people are correcting a lot, you can't really tell which characters are particularly hard to enter or which characters people fix a lot if they correct the errors. Most people correct almost all of the errors. So often the uncorrected errors are very small percent, and the corrected errors can be quite high. Anybody have any other answers for uncorrected versus corrected? That's pretty much the main point. And then the Palm graffiti alphabet was much more accurate and much appreciated. All the writing was in the same place, so it was more efficient. The strokes were carefully designed to be highly accurate. All of the strokes except for X were a single stroke or unistroke, so they were faster and more accurate. Something nobody mentioned was that they had multiple options for each letter, so that you could draw an E like 3 or 4 different ways. That made it more popular and more accurate. Anybody have anything else for the advantages? Okay. Almost everybody got a few of these wrong. There were 24 little boxes, and this was 6 points, so they were 1/4 of a point per box. So I just summed up the number of boxes you got wrong and divided by 4. Some people had no idea what these were, even though we went over these models in 2 different lectures. We talked about them in both lecture 11 and lecture 13, if you want to go back and check. There was a whole bunch of talk about both GOMS and the keystroke model. So the keystroke level model is a way of modeling or doing a mathematical calculation on how an expert could perform this task by counting the keystrokes that they have to do. And keystrokes also counts button presses and so forth. So it ways to give you expert behavior, expert performance on a specific task that you can use. And so it obviously provides timing data. It helps you find places to optimize. It has nothing to say about the look of the interaction because it's only about the performance. You can certainly evaluate an interface before it's implemented because it's a mathematical model. It does not require any human people because the whole point is it's a mathematical model. Selection rules is not that one. It does not support tasks where you have no goal like browsing because it's only about expert performance. Browsing is I don't know what I'm doing, I'm just looking around, so you don't have a particular task in mind, so it can't say anything about that. And it's only for expert performance, so it doesn't count for the last one. GOMS is another model. Who remembers what it stands for? G is goals, O, operators, M, methods, right? And selection rules. So that kind of gave you away this answer. Operators and selection rules was only GOMS. It was in the name, so that was should have been really easy. GOMS is a way of also modeling systems that's a little more sophisticated than keystroke model, but it has pretty much the same answers across the board except for this one. Otherwise, it's pretty much the same as the other one. And it also permits the study of different levels because you can model people trying to understand an interface with GOMS that you can't with keystroke model. And finally, user studies is when you put a person in front of an interface, so clearly it has to be implemented. But I also actually counted either answer for that because, of course, you can do paper prototypes and do a user study of that. So basically, any answer you gave for this box, I counted as correct. It was kind of something I realized later and was a little bit weird for that one. But otherwise, you can get timing data. You can find places optimized. You can evaluate the look because you have the interface in front of somebody and see how they like it. You can evaluate it. You cannot evaluate it. Well, we just said that. It requires people. It doesn't do this. You can have people do browsing, and you can certainly test novices and experts. Okay? So that's the midterm. I'm certainly happy to if I graded something incorrectly or if I added it up wrong or anything like that, I'm happy to look at your answers. Okay, the next important topic is the final projects. And it may seem like we're in the midterm, since we are, but surprisingly, there's really only about a month to do the entire final project. So your presentations are going to be April 21st, which is basically 4 weeks from today, right? So even though we're at the midterm, there's only 4 weeks to do this homework, the final projects, which is twice as long as a homework time. So there's really no time to be fooling around. Okay, so we kind of have to get started on the final projects right away. And so I'm hoping that you, or I'm requiring that you have your ideas for what project you want to do already by Wednesday. Okay, and the way we decided to do that is for everybody to enter their idea for what they want to do into, how do I get this to show me little icons? Got to close a few things. Side. Yeah, that's a good idea. So everyone should go to project, and I've put this this little 4-questionnaire thing here, and so everybody should copy this and enter, I guess down here in follow-up, your answers to these questions. Okay, you should do that today or tomorrow, and then on Wednesday, Jeff and I will try and make sure that everybody has a project to do. So everybody should fill this out. If you want to work with somebody else, you can mention that in the last question. Yeah, if you have in mind others to work with on the project with you. If you want some other people but don't know who, then just describe what kind of people you're looking for. Like, I'd really love to have an implementer working with me, or I'd really like somebody who knows statistics, or I'd really like somebody who can do pretty graphic design. And so in order to help with that, then in the third question, you need to list your own skills. You know, what can you do? Can you do graphic design? Can you do programming? If so, what kind of languages and so forth? And then the top one is your idea for what project you want to work on, or if you don't have something in specific, then say what area you want to work on. You know, I'd love to work on a new interaction technique, but I don't have any particular ideas. Or I'd really like to work on history, or I really want to interview people. Okay, so if you don't have any particular idea, then write down your area. And, I hate how this just disappears everything you need to know. Where did it go? So on the course main page, back at the bottom of the main page, these are the final project ideas that have been here all along. We've added a few new ones, so if you just looked at them before class started, then you should go back and look again. And so we'll be delighted to have any of these. Another one we added that's new is this idea of taking the data from the homeworks and analyzing that, because we haven't really done anything with it. So we've got all the scroll data, we've got all this text entry data, and we've got all this clicking data. Maybe it'd be interesting to analyze that or to do a report based on that. I think there's plenty of projects here. If everybody in the class picked one, then that would be fine. If you want to make up your own, that's also fine. A few people have emailed me some random ideas along the way, and I felt that a bunch of the ideas were, let's go back, were a little bit too much like applications. And remember that this has to be an interaction technique. So saying I want to redesign a new web page, for racquetball scheduling or something is not an interaction technique, right? It's certainly a good user interface design project, but it's not an interaction technique. So I want to do a new menu. I want to do a new kind of scrolling. I have this great new idea for text entry. Those are interaction techniques. So hopefully everybody by now knows what an interaction technique is, and you can come up with your own ideas, and that's perfectly reasonable. We want everybody to be in groups, no more than 2 or 3 people. And also each group has to do something different. So if 3 people, if 7 people want to interview Larry Tesler, then some people aren't going to get to do that, right? So we need to make sure everybody's doing different things. And that's one of the reasons we're using the public forum in Piazza. So you can look and see what other people have already signed up for. And if you like what they've proposed, then you can say, can I group with you with that? Or you might say, shoot, that was the project I wanted to do, now I have to think of another one. And if there are too many people on one, then we'll be in touch and try and negotiate a different project. Okay, and then what do you have to do? There's a very detailed explanation of all the deliverables for the projects here. And also there's a summary of the schedule at the top. Okay, the first deadline is Wednesday. We're going to help you form your groups by next Monday, a week from today, so you can get started right away. And there are already deliverables a week from there. Because remember, we only have 4 weeks to get through this whole project. So 2-page proposals, interim reports, presentations, and there will be penalties for being late on all these. These are homeworks. They're part of your grade. Okay, so don't just blow these off. These are real milestones that we're going to enforce. Unfortunately, towards the end of the class, both Jeff and I, and probably some of you, are going to be away at the CHI conference. So that's the last week of class. So there's no class the last week of class, and so the presentations are the week before that. So that's one of the reasons that this is kind of a compressed schedule. Haven't quite decided who's going to be on which days or how we're going to work that out. I probably will just do it randomly or something. If anybody has any thoughts on a fair way of doing this, so some people will get an extra 2 days to do their presentations. But we also wanted to give you plenty of time to write up really nice reports. And so you actually have until during exam week to finish the written reports. Okay? And for those of you who are graduating, we have to grade these pretty quickly. So I don't want anything late. Okay? There probably will not be a generous late policy for the final report deadline. If you're planning to leave early, that's fine. Just turn in your report early. Certainly never a problem with turning things in early. So your presentations, we're going to want your slides. We're going to put them up on the web. So definitely worth putting some effort into that. But then your final reports will be. And then there's details about all of these deliverables and how long they're supposed to be and what they're supposed to be like and what the content is in here. And we're happy to refine that if you find anything that's ambiguous. Okay? Any questions about the final projects? I'm hoping that, there's a whole bunch of really interesting topics here. I'm hoping people will, do really interesting things with them. And as I mentioned before, we have a deal with the Interaction Design Encyclopedia to, if somebody does some history stuff, to put things up there, or an evaluation of a current technology. We also have the option of changing Wikipedia pages, because almost all of them about interaction techniques are awful, and definitely could use a lot of help. If somebody's creating something new or doing a new kind of evaluation, there's the opportunity to have a conference paper out of it if you're interested in that kind of thing. We can continue to work over the summer and submit it in the fall. If you invent something new, any work you do in this class is considered your own intellectual property. So if you invent anything new, you're certainly welcome to do anything you want with it. You can patent it, you can try and sell it, you can make your own startup out of it or whatever. So those are all available if you come up with something cool. So we'll be interested to see what you come up with over the next couple days. Okay, anything about that? Okay. So I have office hours tomorrow. If you want to discuss these, I'm just going to be there. If you want to talk about email or through Piazza, you can definitely talk to me and Jeff, or me or Jeff, by email any other time. Jeff's has to move his office hours so they're not on Wednesday. It would have been after class anyway, so it's too late for this part of the assignment. But Jeff's busy on Wednesday afternoon, so it's going to be Friday. And we're both happy to talk about project ideas. If you want to talk about homework 3, you can ask Jeff. If you want to talk about the midterm, you should ask me. Okay? So that took a while. So there's not much time left for the topic of today's lecture, which is 3D interactions. So this is things in the real world. If I have some actual object, like say an object, then I can move it around in 3D and tilt it, right? Whereas a mouse only moves around on the desk on a flat surface. So the mouse is a 2D kind of thing, whereas what we're talking about is 3D. And it turns out in 3D, a mouse moves around on the desk, which is 2-dimensional, but it turns out 3D is at least 6-dimensional. Okay, so it's left and right and so forth like on mouse, but it's also up and down. So that's the 3rd dimension. But it turns out that in 3D, you almost always have to deal with rotation. And there's 3 rotations. There's this way, and there's this way, and there's, I forgot one. This way, and this way, yeah. But this one's kind of symmetric. So, but there's a sticker, so you can see the difference, right? And those in 3D have actual names, roll, pitch, and yaw. I don't remember which is which, so you don't have to either. But it comes from aviation, where obviously it's really important for the airplane to know how it's oriented. Another thing really tricky about 3D is where is the camera? So I'm sure most of you have played these 3D games, which tries to make sure your character is always seen in the scene. But if you've ever done any 3D modeling or 3D work yourself, you know it's really easy to have the camera pointing in the wrong direction and you can't see what's going on. And so there's a camera pointing at the figure, and as you move the figure, or if you have a complicated scene, you have to figure out where you want to look from in order to see the figure in the right place. So in addition to having all these dimensions for your figure, you also have the same number of dimensions for the camera that you have to control as well. It turns out, even though we work in the real world, which is obviously 3D, and it seems like people would be really good at 3D manipulation because you do it in real life all the time, people actually are not very good at 3D manipulation on a computer. And in real life, there are a bunch of tests. If you show somebody a figure and say, rotate this in your mind, and what does it look like from the back? That's a typical question in an IQ test, because it turns out for average people that's really tricky. And that doing mental rotations of what something looks like from the other side, where is this not symmetric, all sorts of questions like that, turn out to be really hard for people, and they're a very advanced cognitive skill. So if I asked you, rotate this around in your head, and where would the leg be? Then you might actually have a lot of trouble figuring that out. And so that's not very easy. And of course, most of the input devices we're used to dealing with are 2D, and so mapping this 2D into a 3D location is really tricky. Another thing about 3D is, unlike graphics, what we've mostly dealt with, which is a rectangle, almost everything in 3D are these really complicated, highly hierarchical shapes, right? And so this girl is a lot more complicated than a plain rectangle or a circle or something. And in this room, you've got all these different parts, and they're soft, and there's shadows, and occlusion, and all sorts of complexities. So inherently, you're generally dealing with things that are much more complicated than just a circle. So there are lots of reasons why 3D is a lot harder. There's this nice article that I put in the readings that describes a lot more of them. It's actually a panel from 1994. So when you're trying to pick something in 3D, if I wanted to point at one of you, right, it's actually a little ambiguous who I'm pointing at, right? So you can't quite tell if I'm pointing at you or you or you, right, because there's a little bit of ambiguity. If I had a laser pointer, then there would be a dot on somebody's chest, and you could tell better. But there's a lot of ambiguity, and there's occlusion. So if I'm low, I can't actually point at some people because they're in the way, so I have to move to the side. So 3D picking is actually hard because of occlusion. Also hierarchy, if I wanted to pick Sam's eyeball, you know, am I pointing at his eyeball, or am I pointing at his head, or am I pointing at his hair in the back of his head? You know, so there's this hierarchy, and you know, it's a lot more complicated than a simple group or character text, right? Things like that. There's all these different levels that makes it very difficult. There's, you know, in conventional selection, you have these widgets, which we're all very familiar with, and people have tried to do that in 3D, but it's much more complicated, as we'll see. And you know, where do you stick all these widgets in the scene? You know, if you wanted to have a menu in a 3D you know, landscape, you know, where would it be? You know, would we put it up on the wall? Then it has to be reachable and stuff like that. And this particular article from '94 discusses the difficulty of doing things in interactive speeds. That's still an issue, obviously not as much. There's a lot more we can do in interactive speeds even on a laptop, much less special purpose computers. No one in the room has an Alienware, but you know, my son is you know, wanting one of these enormous laptops that has all these special purpose graphics processors in it that are really heavy and have really short battery lives. But even today's general laptops are pretty good at stuff, but you still might have different kinds of, you know, when Pixar makes movies and so forth, they can't do frames of the movie in interactive speeds. They have to have simulations. Another kind of meta issue about 3D is where to display it. The obvious first answer is just on the screen like everything else. So desktop screens in the usual way. Another thing are these giant displays. So we saw a giant display way back from the 70s, and the STMS system from MIT Media Lab, they had this great big display. Often you have things called caves, and this reference seems to be the first time that word was used. But the idea is that you project the picture not just in front of you, but also on the side, and sometimes the ceiling and the floor as well. And so it makes it more like you're inside this environment. So these people are in a room where the pictures are on all, sometimes even behind you. So then it can be on all 6 walls, 6 sides of the space in which you're in. Usually the back wall doesn't have anything on it, but it's not uncommon. And anybody been to Disney Quest in Disney World in Florida? They actually have one of these that you can go into. It's a ship ride, Pirates of the Caribbean ride. And they project, you know, the sea on all of the walls and the ceiling, and you're actually standing on a pretend ship, and you're firing cannons at stuff, right? So, but it's a very effective, simulation. And then the third choice are what's called virtual reality goggles sometimes, or visor or something like that. And they put this thing in front of your face so you can't see anything except what's on the screen. And typically they'll have head tracking. So as you move your head around, the scene will change, hopefully in sync with moving your head, although there's almost always a lag, so people get seasick because it's really hard to keep up. So that's the idea of virtual reality, is where you can't see anything in the real world. All you can see is this pretend picture. And then augmented reality is similar, except it's superimposed over the real world. So you can see the real world and you can see the computer-generated picture in front, or superimposed over the real world. And there's a lot of examples going back through history of that, but that's, who knows what this is? What's this a picture of? Google Glass is, you know, currently or soon to be a commercial product that is an augmented reality system. So it doesn't prevent you from seeing anything else, right? There's nothing in front of this eye at all, and this one's actually see-through, but it superimposes it over it, so it's quite different than that. That's called augmented reality as opposed to virtual reality. Okay, so that's kind of the choices we're looking at. And then there's a variety of ways people have come up with to control or, you know, to input things in 3D. The standard one is just to use a mouse and figure out some way of taking your 2D mouse and making it work in a 3D world. And so we'll see a bunch of research and commercial systems that deal with that concept. The next one is the idea of taking the mouse up and being able to move it around in 3 space, right? So I remembered that that had been called a bat, but you can't really search for that on the web. So luckily, I did a bunch of searches for a 3D bat, and I came up with all these bats. But eventually, I actually found the article that mentioned that first time, so that's what the link goes to. So a bat, of course, is a mouse that flies through the air. If anybody speaks German, the German for bat is actually Fledermaus, which apparently means flying mouse. Anybody here speak German? Okay, good. Then you don't know I didn't pronounce it right. So the idea of a bat is you take the mouse up in the air, and as you move it around, the computer can measure all three dimensions. And usually 3-dimensional mice are also 6 degrees of freedom, so if you tilt it, it knows that too, right? And so nowadays we do that all the time with our phones, with accelerometers and things like that, but most of the systems we'll see work in a different way. But that's the general idea, that you can have a 6 degree of freedom to basically pick the mouse up off the table. Another common way that's becoming more and more common is you don't need anything in particular. There's just a camera watching you in 3 space. And so everybody knows what's the popular current example of the camera tracking people? The Kinect, right? The Xbox, Microsoft Kinect is a camera looking at you, and as you move in 3 space, it's watching you. So that's a camera-based thing. And sometimes these will have special dots you have to put on your body or something to make it easier for the computer to track you, but it's basically just a camera. Another popular one is that there's something that's on a bunch of gears or motors, and you're moving it around, and it's trying to track you. And I'll show you some examples of that. And then, kind of as a summary, there's sometimes physical objects that combine a bunch of these together. So these are kind of the choices that you have in terms of 3D manipulators, and we'll look at examples of these. So here's some, the first example was boxes full of knobs. If you remember the Sketchpad, it's kind of like that, where you just have a whole row of knobs. And I was trying to find a picture, because I remember that the 3D computers or the graphics computers of the 70s actually sold knob boxes, but I couldn't find a picture of it. So Silicon Graphics was a company that produced high-end graphics machines, kind of obvious from the name. And everybody in the 70s and 80s who was doing graphics would get an SGI box, and they had some knobs, and I couldn't find any examples of those. The next one is a Polimas sensor. So it's a really old company. It started in 1969 already with 3D trackers. So amazingly, it's still in existence with the same name. So almost everything, in computers has gone out of business or changed names or been bought out by somebody else. But Polimas is still there. And they're still selling products that are quite similar to these original old trackers. And basically, the idea is that there's this thing that you wear that's on a wire. And nowadays, of course, it's wireless, but it's basically the same idea. This little thing, and it puts out some sort of magnetic waves. I don't know the physics. And then separately, there's this other box, which is the sensor. Here, it's this one. And the sensor can tell where the little box is in 3D, plus all the different tilts. And it works by magnetic waves, mumble, mumble. I don't really know the details. The key point is it has a fairly limited sensor area, typically about 2 or 3 yards, square yards that it can measure things in. Typically, you can have more than one, and they're tuned to different frequencies or something so that they don't interfere with each other. And often those would be attached to things. So this is a glove, and it has one of those sensors in the wrist. Okay, but the glove is also instrumented, so it can tell what pose your hand is in. So the key word there is pose, which is kind of how I'm holding my hand. And there, as you'll see, there are a whole bunch of interaction techniques that say, if I do this, then that's something, or if I do this, that's something else, and so forth. So you want to know kind of where the fingers are, if I'm pointing at something versus doing something else. you can imagine that the computer would want to know the difference. And so these gloves, what's happening here is these sensors are detecting, when your fingers are bent and how far apart they are and so forth. So it's called a data glove. It started around '82. It was very popular for a while with all of these virtual reality systems, and would measure all sorts of things about your pose and finger bending. Nintendo actually came out with a cheap version called the Power Glove as a game system in '89. It was a total flop as a toy. They only ended up making 2 games that really made good use of it. They also encrypted the signals coming from the glove to the computer, to the game console. So they tried to keep people from doing research with it, which was a bizarre decision. But of course, some researchers actually managed to reverse engineer it somehow. In particular, Randy Pausch, everybody know who Randy is? Former HCI professor here. One of the things he became famous for back in '91 was this paper called Virtual Reality on $5 a Day, where he, at the time, it was very expensive. You had these big caves that people would make for $1 million because projectors were really expensive, and you had to have a special room. Sensors were really expensive. And so he reverse engineered the signals coming out of the Power Glove, which was, $30 or $40 game system, in order to try and, make that cheap. And then he had a cheap way of doing these virtual reality goggles that covered up your face. So that was one of the earlier systems that he created. And Nintendo was very much against people doing that for some bizarre reason, and that was one of the reasons it didn't become popular. Minority Report, everybody knows this movie, fairly famous movie with Tom Cruise. When he wanted to interact with this giant display, he put on these special gloves that had blue lights on the fingers. For some reason, all science fiction, if they do something in blue, it's the future, right? So apparently we don't have enough blue today, so everything in the future will be blue. And sure enough, there were little lights on the fingers that were tracked by this, futuristic display. And he did all sorts of gestures, and that caused the display to do stuff. There was actually a guy from the MIT Media Lab who was listed in the credits as a science advisor to the system. And so the science in this part of it, at least, in the displays and so forth, is pretty achievable, even back then, certainly today. Tracking the fingers and doing gestures to cause this display to do stuff is perfectly reasonable. And they actually implemented one at the Media Lab to show it wasn't that far-fetched. The other parts of Minority Report where you can see the future, obviously, are a little bit less easy to implement. And I don't know if you've seen modern science fiction shows like Almost Human. Is this robot, android thingy, police person, but they're still using this kind of display where you wave your hands in the air. If anybody's ever tried to use a system where you spend all your day waving your hands in the air, it's actually very tiring. It's much easier to use a touchpad or a mouse where you can rest your hand on the table. So, this waving your hands in the air stuff is really not very good for anything you want to do for a very long period of time. Motion capture is really big in the movie industry. And so there's lots and lots of movies that are made with motion capture, with actors like Gollum from the Lord of the Rings movies was made this way, and a lot of different creatures. And typically, in current systems, they require that the actor have a whole bunch of dots on them to make it easier for the cameras to detect them. And they typically will use what's called infrared cameras, which look at a kind of light that's, that the eyes can't see. It's basically heat. And typically, these balls will glow really strongly in infrared light, and so it doesn't get confused with your clothing or anything else in the room. And so then the cameras will detect you in 3D. As we mentioned, the Kinect uses the same principle. There's two cameras in the Kinect. There's a regular color camera, but there's also an LED light, and I don't remember which one's which. The LED is infrared light that shines out in the scene, and then one of the cameras is an infrared camera. And that's the actual one that's doing the 3D tracking. And then the color one is used to superimpose a picture of what's in the world on top of the 3D scene. And so this is the old one, the 360. There's a newer version of the Kinect that works much better, higher resolution, and so forth. And I guess Jeff is going to cover the Kinect in a little more detail in the next lecture. The Leap is actually a bunch of cameras pointing up. So it's pretty much the same technology. There's an IR LED that's shining out IR light above it. And as you're moving your hand, it's looking at your hand with cameras. So these are all camera-based systems. I mentioned this ARM idea, where there's a mechanical connection. The original one was the Phantom, and that's actually, this is the current version, but that's been around for a while. And what happens is that it lets you move in 3D, and all the joints are, sensed, so it can tell what angle everything is in, and so it can tell where the pen is in 3D, so it can be up and down or around. And it also has motors, so it can do what's called forced feedback. So if it's trying to pretend that you're drawing on sandpaper, it will actually vibrate the pen so it feels like sandpaper. Or if it's pretending that there's a box in the world, then as you try and move, it'll say, nope, you can't move there. And so the motor will stop the pen from moving in the area that it wants you to stay in. And so all of the joints and so forth have these motors that give you feedback. Yeah?
Are these usually stable? So like the bat doesn't stay where it is because you put it back down on the
Right.
table. Is this stable?
Yeah, so it's up to the programmer. This particular pen is heavier. I mean, if you turn all the motors off, it will actually fall. But you can also make the motor stiff enough so that it'll just hold it wherever you leave it. So in the case of the Phantom, it's definitely up to the programmer to decide if they want to make it stable so it stays where you leave it, or if you want it to just go back to a... and there's actually a picture on this guy's website of the home position, which is where the pen is actually tucked in to the device. This one from Falcon, I think I played with this at a conference. It's kind of more like a rate-controlled joystick in that it doesn't move that much. So as you can tell from these joints, they don't have a lot of movement that they can do. It's just a little bit. And so I don't really remember whether that one returns to a home position or not. But this one is designed for gaming. The reason this is such a honking big base is that it turns out you need some really powerful motors to do this kind of thing. So you're never going to see one of these that are battery powered, because in order for your hand to feel like it's actually stopping your hand, it needs a pretty powerful motor in order to, because you're pretty strong. And so that's part of the issue with these guys. And some of these have been combined into special purpose things. So this is an old one also from Randy Pausch's group, where they took a Polema sensor and put it on a doll's head. And then they put another one on this, this other thing that kind of looks like a knife or a plane. And the idea is if you have a CT scan, then you can look at the head at the scan from any angle in any location. And it's kind of tricky to find where you want to see it. And so the idea is that by holding the head and the thing, you can say, okay, I want to see it from here, I want to see it from here, right? And so you can much easier get an idea of where you're looking at the head from by actually physically moving these devices. And this is, what do they call it, a marionette. That's, you can, as you move the legs and so forth, the computer knows exactly where you're doing it. So it's kind of a more sophisticated version of this guy, right? And you can use that for making any pose you want. And the computer can do the same. It can pose it in any position because it has force feedback in all the joints. And there's a bunch of different levels of these, and these actually go back in history fairly far. I think in Jurassic Park they had one of these that they used for controlling the poses of a lot of the dinosaurs. Okay, but what about interaction techniques? So far we've just been talking about input devices. How do you actually interact with these things? And Sam, when he was giving his little demo a few weeks ago, talked about this 4-panel display, which is kind of the state of the art and probably what most animators use today. It's basically a conventional mouse on the table. And as you're manipulating the thing, you're seeing it from multiple views at the same time, so you can kind of tell what you're doing. But the mouse only works in 2D in whatever window you're looking at, right? And so if I'm in this window, then I'm going along these two planes. And if I'm in this window, then I'm going along the other plane, which is this plane. And there's this plane and so forth. That way you can get more control while still having only a 2D view. Turns out it takes a lot of practice to know what you're doing in these, and people are turning things all the time to try and get the right perspective. And there's been some approaches that tries to go beyond that, and these are fairly special purpose, so they don't work for everything. There's a cool one that just works for rotation, where and it tested really well. It was very high performance, and people understood it really well. And basically, the idea is that you pretend that the thing is surrounded by a sphere, and if you go this way, then it rotates the sphere with your finger. If you do it this way, it rotates it that way, and then you can also grab it and rotate it this way. And so if I want to rotate across, I just go across, and if I want to rotate it around, then I can go around the outside, and that will rotate it like this. And so you get all 3 degrees of rotation that way, fairly straightforwardly, and typically you'd go into a different mode to do translation in the same way. And so it's a fairly clever way if you have a fairly simple scene and you want fairly simple rotations of using a mouse to get 3D input without having to go to multiple screens. There are a variety of other ways you can do that. The obvious one is just to have multiple sliders. You see a lot of systems with gazillion sliders all over the place. It's kind of tricky. Menus is an obvious one. Button modifiers. Maybe you've seen that where you push in the left button and that makes it do X and Y, and you push in the right button and that makes it do X and Z or something like that. Well, why not just have handles? In regular 2D graphics, we stick these handles around the outside of something, and there's this other handle on the top that we use for rotating, right? And that's pretty simple for simple graphics. And you can imagine in 3D, there's a lot more handles that you need. And so this is an example of 1, 2, 3, 4 handles that you can use. They call it a rack. And so if I want to move it this way, then I use this handle. And if I use this handle, I can squish it by moving down. But if I wanted to rotate it, then I would turn it this way and then pull on the handle, and that would rotate it. So you could twist the object using the same handles and so forth. So by sticking these handles around the objects and then moving them in various directions, you can twist, pull, distort the objects in all the different directions. But of course, then the issue is, well, now you have to have all these handles, and the user has to know which is which, and which of these does rotation. It's pretty obvious from that display. You probably would be able to guess which of these handles does rotation compared to which one makes it bigger and smaller and which one moves it. Whereas in the 3D picture, it's not quite as obvious. If I want to twist something versus stretch it, how would you know which handle is which? And there's a variety of other research systems. So another one of Randy's ideas was to have this miniature, like a dollhouse that you hold in your hand. And so there would be a miniature person. So there's a avatar in the house, and you actually pick up the avatar and put him where you want to see, and then the big scene that you're looking at changes proportionally. So it's a way of controlling the camera that's a little more straightforward. Another cute idea that came out of Randy's lab as well is sometimes called a head crusher idea. And this is kind of the standard thing. If you go to the Leaning Tower of Pisa and put your hand up and take the picture from exactly the right angle, it looks like you're holding it up. So it's basically applying that to 3D manipulation. So if I go like this, then it looks like I'm holding Sam. And then I just have the computer recognize that. It draws the hand in the scene. So it knows what the hand is bracketing. And then you could use that as a way of telling the computer what you want to select, and then you could also squish it, change its size, and so forth by having the hand in the scene itself. And he designed a bunch of interactions, so moving, you put your hand out and you pick it up, you know, resizing, selecting, and so forth. So again, it's measuring the pose of your hand, remember, which we're getting from the data glove, and also this particular position of the hand in 3-space, which you can get from the Polimas sensor. Here's another example of having 3D widgets or control handles on an object. This is a nice research paper where they put a cube around the object you want to manipulate, and there's a great video. I know. Maybe I'll stop here and we'll show some of these videos next time because they're kind of fun. So we'll, I hate to skip them because there's a bunch of really good stuff. Not very long, maybe 10 more minutes. We'll go at the beginning of the next lecture. Okay.